I'm going to go ahead and start the conversation here. So this is based on a project that we started earlier this year, and I'm going to kind of give a background on why we started it, what its functional capabilities are, and why we had to do it. And so let me jump right into kind of that agenda perspective. So I'm going to start with the what. What is the project that we started with in ODL, why we did it, why it's needed, and then jump into how we're actually implementing it. I've seen a couple of the sessions here where they're actually pulling up CLI and running demos. I'm not going to do that. I'm just going to give more of an architectural kind of perspective on this. This has been a rather interesting experience for us as we're new to ODL. We've taken this approach second after doing a lot of work with Open vSwitch, and the team members there throughout the experience of developing that has been a lot of fun. And as we got the implementations of OVS done, and that's now part of the upcoming 2.4 release for this functionality, we've had to now move on into the controller space to make sure that we can get a holistic management of that. All right, so let's kind of jump into the project description. So what we started was basically a way of managing a distributed LLDP approach. Normally, the way ODL will actually work is that anything that happens as communication between the vSwitch and any of its actual physical switch neighbors has to all be sent up to the controller. And while that's a nice way when you want to know exactly what's going on inside the virtual topology, and you want to have a ability to control that topology, it also creates a tremendous problem of scale. Right? And so LLDP and all these other protocols, trying to get all the LLDP messages coming up and bridge that up into a centralized place works up to a certain point. But once you start getting into the level of hundreds and thousands and tens of thousands of these devices out there, you start running into issues about how you're going to scale that and manage that in a large-scale environment. Additionally, what we found is in a lot of deployments around the world of a protocol we called SPB, which is down there at the bottom, 802.1AQ, is it's used in a lot of data centers. It's also used in a lot of campuses. And we found that it does a lot of the automation and capability that a lot of data centers are asking for. And the last piece that was missing was the ability to automatically attach the edge devices directly into the fabric. And now, so some vendors are taking a perspective of, well, let's just abstract that by creating overlay tunnels. This will actually allow you to integrate that into this thing. But SPB actually gives the same functionality directly at the hardware level. You actually have complete virtualization. We're not limited to 4,000 VLANs anymore. We actually have 16 million. And we have integrated routing in it as well. So with those capabilities, we're actually able to forward and create LAN environments, anything we want, across a physical infrastructure and do it in a couple of milliseconds. So you just configure one end, you configure another end, and the network automatically creates a LAN in the middle, irregardless of the scale. This isn't 4,000's tiny little data center networks anymore. These are now very large-scale environments. Now, the scope of where we're trying to get to this thing is kind of described there, is that we want to be able to configure the actual vSwitches to tell the network what service they want delivered at their point. Because oftentimes the network infrastructure in place is not owned by the same team that's deploying the vSwitches. Now, also the network team itself is not actually managing the vSwitches either. And there's always this kind of separation of the two environments versus the actual management of the environments. And so if you had the ability that a network could be created, stabilized, can deliver any service anywhere at any moment, and then the applications and the virtual machines themselves can be turned up, moved, deleted in any combination, and automatically signal to the network that they need a CRUD application happen to create, update, or destroy kind of operation. Then the network would automatically deliver that and deliver it within milliseconds, and also deliver streams of connectivity in milliseconds without affecting performance. You've got a good, powerful thing there. And so we worked with a few entities out there to try and make sure we approach this thing as open as possible. So we tried to make sure that we were being very good open citizens. So we used open standards. We actually took the idea of how we would auto-attach these things to the network and created a pre-standard, long before pre-standard, actually, a idea and put it into Open vSwitch, so it became open source. We actually published a draft into the IETF. You can look it up by my name. And that draft has now become 802.1 QCJ in the IEEE. And so this will actually become a standard part of 802.1q as a way of automatically signaling from a VLAN or non-VLAN capable device, because it doesn't have to be a switch, a vSwitch. It could be, for example, an Internet of Things device that simply can run LLDP. And that will automatically signal to the network that it needs a service. And so a use case of this thing is that we discovered over some really large deployments and even small deployments. At the Sochi Olympics last year, we discovered this ourselves as we deployed this. This is one of the more public examples of shortest path bridging running in the wild with this entire network. Everything you watched, if you watched the Olympics, by the way, was running over SPB. There was no MPLS, there was no OSPF, it was all SPB doing the routing and the switching. And it showed us a lot of things because it's a great example of the modern day environment, both data center, campus, and metro, is that virtualization is no longer a nice to have, it's a requirement. There's a lot of concepts and discussions about there about what microsegmentation is. If I look into a hospital, for example, there's a ton of microsegmentation. The MRIs, for example, are locked away from the pill dispensers, which are locked away from your guest wireless. Those are great examples of true virtualization have to be enabled. And they can't come at the cost of an MPLS core, right? They got to be done quickly and at hardware level and managed centrally. And so that's that nice combination that we see out of a Fabric plus an SDN. It shouldn't be a Fabric or an SDN. And a lot of the customer deployments we've seen out there, that's exactly kind of the case. But when they're looking at the world of what are they actually trying to do versus just a cool technology, well, the cool technologies are fun for us to play with as engineers, but they don't actually solve a business problem. And so the business problem we're trying to solve is how do we automate the attachment of these devices because they're exploding. And at the Olympics, a great example, we went from 0 to 40,000 users in less than 12 hours. That was a drop in a bucket compared to the actual total number of devices connected to the network. Total number of devices in an environment actually numbered in the hundreds of thousands. So the users were a tiny little blip on our screen as far as devices we had to worry about. And by the way, those 40,000 users were bringing in 3 to 4 devices. Right, so really it was 120,000 devices. Still, that was a small amount of the traffic we worried about. The large amount of traffic we worried about is the trash cans that were connected to the network, the clock that you were watching the games on, right? The camera. Right? All these little things that are connected inside of this environment actually needed real-time applications, and those things would not accept an amount of downtime. And then if I look at a hospital, they have the same problem. Stock exchanges, the same problem. Subway systems, exactly the same problem. And the idea that our networking staff would be able to actually go out and configure every port on the fly for every device was untenable as well. It would have taken a fleet of people years to do. And so by taking more of a Fabric plus SDN approach, we were actually able to do it with 2 people in the NOC only. For the entire event, 2 people, that's it. And so it's kind of like running 7 Super Bowls every day nonstop for 3 weeks. Now this is not special to the Olympics, I just use them because they're a public example of all the other deployments that are out there. But it showed why we needed to solve this problem. IoT is no longer a buzzword, it's a real problem in real environments that we have to solve as a way of getting the humans out of the machine and make them more of the policy drivers. And so policy becomes a critical component of it. Now, driving down now into more of the how versus the why, this is more of the architectural kind of perspective of a forwarding example. So I want to kind of pull this out from a different perspective than I've seen all day talking about the software models. Those will come in a few slides. This chart, I want to talk about actually what's really going on from a forwarding perspective. And there's a few charts like this kind of move. Essentially, in traditional environments where you're running either normal VLANs or you're doing this new capability of SPB, which has, by the way, been around for roughly around 5 years, you have to, at that red line there between the client and the web server, that's a manual configuration in a lot of previous environments. You'd have to go to that interface and type VLAN 6 mapped to ISID 200, or VLAN 400 mapped to ISID 1,016. That's where the crux came from. It's also a crux for even traditional Ethernet environments if, God help you, you're still trying to use spanning tree, right? Which you shouldn't be. Even the IEEE isn't using spanning tree. We're moved on to SPB now. The point where we had to get to this is we wanted to have the ability that we no longer had to configure that VLAN on the access port. We want that to actually be automatically signaled up. And we also want to be able to support is what happens if there's not even a VLAN there? What if there's a complete port and the device that's connected doesn't even understand what a VLAN is? And so that's the fundamental crux of this. We can connect any LAN to any point at any moment easily once you configure that ISID. In fact, SPB is based on ISI, so I'll kind of get in a second about how it works. But that automation, that connection, is the fundamental thing that we worked on here from a data plane perspective. So we started from a foundation of how we're going to make this work in the real world, and then grew that into how we're going to manage it. And that's kind of where we are now with the Open Daylight plugin that we're building. And so it's all based on a PBB-based functionality of knowing these ISIDs, because now we got 16 million forwarding LANs that we can do at hardware speed. We don't have performance problems. We can use the native VLANs that everything out there already understands, the same Ethernet that your laptop understands, the same Ethernet that can plug into this. And by the way, every virtual machine on the planet already supports this. There's nothing special that has to happen. There's no craziness that has to happen. There's no relearning of new technologies. It's still Ethernet and still VLANs. It just plugs into a new flexible kind of network infrastructure. The other nice thing about it is that because the ID that we use to get off of 4,000 VLANs to 16 million ISIDs is 24 bits. So it maps really nicely to the overlay protocols. And so we can actually mirror and connect them together natively as well, some pretty cool ways. So for those of you who don't know what SPB is, let me kind of give a quick background real quick on this thing, is that SPB is essentially the new way of doing spanning tree according to the IEEE. Right? It is 802.1AQ. Actually, it's officially 802.1Q now. It's actually been subsumed up in the Q. And it's a link state way of controlling topology. It's IS-IS, managing VLANs and managing this new VLAN ID we call an ISID. And so instead of having 4,000 VLANs, we have 16 million VLANs. And we can reuse the VLAN ID at any given place in the network. So that means I can come in VLAN 6 and go out VLAN 600. And it's still the same LAN because it's really the ISID ID. And so because it's a link state protocol, I've got all the benefits of link state. I've got super fast propagation of a new topology. I got super fast propagation of a failure. I've got immediate knowledge of a new configuration within the environment. And because it's a link state, I no longer have to provision hop by hop by hop. That world is gone. And so in all the deployments out there, most of the time they point out that there's a 10 times cost reduction of running a network using SPB versus other technologies because it's one protocol, one fib, one configuration. Much simpler, much easier to deploy. But again, you're still configuring that edge port. And so the service virtualization, I kind of want to touch that real quick because that's really important here. The virtualization built into SPB did to the network what the virtual machine did to the server. It essentially turns the entire physical network, a combination of hundreds or thousands of switches, into a perceived perspective by the end client device as one switch. If they try and do a trace route or a ping or anything like that, the whole network looks like one hop. And essentially, these ISIDs, because you provision them on the edge, they create a virtual switch across the network on a per LAN basis. So you have 16 million virtual switches, essentially. That's created from that client perspective. So a VM, and in fact, actually at the Olympics, we had 5 data centers running live, all acting like one virtual data center. VMs were moving across that infrastructure completely unaware that they were going across the infrastructure. They thought they were going in port 1 and out port 2. And that's the way it is every day in every environment that's running SPB today. Now, the problem we had in that environment is how do we automatically know where those things are? How do we automatically attach it so that a network guy doesn't have to configure a port anymore? Or we don't have to do unholy things in management servers? How can we actually tie a protocol with a management system to work together to automate these things at a good speed? And so let's talk about another architectural perspective on this thing is what is encapsulation? So if you've ever seen VXLAN or PBB, they look very similar to each other. PBB has far less in its header, but essentially the yellow header space only exists within inside that SPB ISIS domain. You're forwarding basically on a MAC address. Now what's interesting about this is an SPB domain, the MAC addresses that are inside that domain are only inside that domain. The space inside that cloud is orthogonal to the customers, meaning that I can have 15 million end devices on the edge of this thing and 6 switches in the middle supporting it, or 600. The MACs from the clients are never seen inside that network, ever. The only MACs that appear inside that cloud are the actual nodal MACs that ISIS uses as its nodal ID in the link state protocol. Basically, if you understand routing protocols like OSPF, there's a router ID. The MAC is actually the router ID. So we reuse its router ID in the graph as the actual forwarding address between endpoints. And that creates a whole ton of heuristics that provide performance that we reconverge networks in milliseconds, not link whole networks. And so that ISID is now that new field. Now you see there's VLAN IDs, BVID and CVID. All we really care about here is if you look at the 2 bottom examples, the line signifies this new ISID, this individual instance service ID. That goes up to 16 million. The VLANs become locally significant to the port. I can reuse VLAN 2 on port 1, 2, 14, 16, and 18. And it's not the same LAN because I'm plugging them into different ISIDs. So on port 1, I can go VLAN 2, ISID 600. On port 16, VLAN 2, ISID 600. Those are different LANs. And so I now have 4,000 to the 16 million power of LAN configuration. And because I'm mapping the true identifications to the ISID, on the other end of the network, as shown in the yellow, I can rewrite the VLAN going in and out. And so if you have a multi-domain topology where you ran out of VLAN space in one part of your data center versus another, putting SPB in the middle allows you to actually bridge them back together. And integrating into routing, I get more intelligence about where my subnets are as well, and that creates some pretty interesting things. So fundamentally what happens, though, is that within the architecture as a whole, ISIS, all it cares about is where these ISIDs are. It's a very simple addition. The way that ISIS shares where routes are is the same way as how it shares where these endpoints are. And so just like if you go to any one of these ISIS nodes and configure a subnet, and it automatically announces that into the routing protocol, you go to any one of these nodes and you configure an ISID, it automatically announces that's an endpoint. And then every node in the middle recognizes it's on the shortest path between those endpoints and installs a LAN service between it. You want to add another LAN service in another box, you just go over and configure that ISID, and immediately it's going to be connected to that LAN. That's it. But there's a crux in it, and why we're moving here at ODL is that you still have to configure that in a traditional way. Now, the encapsulation technique there I talked about provides an orthogonal separation between the client and the actual network. But the ISID actually gives us a lot of capability. Now, I want to step into actually a use case of this thing is that if this is a data center, for example, the VMs are going to see this entire infrastructure as one switch because of what that yellow space did for us. It provided a nice holistic way of hiding the infrastructure. You can't get access to it unless you're an actual admin, right? And so if you're in a hosting environment, you have 16 million possible tenants you can have, or you can provide 100 LANs per tenant. And they are completely isolated to each other, and they can be plugged up into a VRF to get true Layer 2 and Layer 3 virtualization. Because you can do a VRF in this without having to do MPLS. All right, so now let's get into the nitty-gritty of what's going on, of how we use this with the actual ODL and OVS capability. Now, so to lead into this thing, to make sure you don't feel like this is vaporware, we actually proved this out last year and created some demo code. And so as I said, we started out with the foundational inside the SPB. Then we actually created some of the demo code, prototyping this out within VMware and an Open vSwitch and a few other places. We ran at VMworld last year to prove that this could be done, an Open vSwitch inside ESX on a physical server. On the right, there's another physical server. And on the bottom right, there was a client streaming a live video stream because there's no demo that's ever complete unless you're doing a video, right? How else do you prove that something's real? And so we had a VLC client going across an SPB environment, streaming to a client. And so the client over here is getting the actual video. I'm sorry, the server was at the top streaming the video. And then what we did is inside ESX, we dragged and dropped the server over to another physical machine. And using this auto-attach capability built into LLDP, it automatically signaled to SPB that we needed a new attachment over on this new top of rack. And the top of rack automatically saw the announcement of this new node over here for this ISID, automatically provisioned the ISID and the port to that ISID, and the network automatically converged in around 2 milliseconds. So the LAN was actually there before the server actually completely moved over, essentially. And then because it moved over to the new physical server, the old configuration automatically disappeared off the old top of rack. And so this was all done before we actually started ODL because we actually did all this in Open vSwitch. And so we contributed all of this code that we did into OVS. And so if you actually want to play around with this, you can see this in OVS 2.4. It's going to be a part of that mainstream, and it'll be there and play around with it. We have a lot of people actually running this. I thought the best example is someone's running this on a Raspberry Pi right now in their basement playing around with these things. We see some pretty interesting ways that people are using this. Okay, so once you start looking at this perspective, now the next question you have to ask is, how are you going to actually manage this in a large scale environment? What happens when it's 1,000, 10,000, 50,000 virtual machines, or it's 100,000 end devices inside of a campus somewhere? This is where we get into how do we use controllers. And so this is where it's not a matter of dogma. For us, it's a matter of use the right tool in the right place. I don't nail a screw, and I don't screw a nail. Right? I use a screwdriver for the screw, and I use a hammer for the nail. And so using the right protocols and techniques in the right place is really critical here as we're looking at analyzing how customers are really deploying things in their environments. Specifically, as we started watching how people were deploying Open vSwitch, how they were deploying IoT. And hey, if you actually look at IoT, what's the vast majority of the operating system running in IoT devices? It's Linux. And so that creates a very interesting problem set and opportunity at the same time. And so in this architecture kind of perspective, at the top we have Open Daylight, and at the bottom we saw a large-scale environment, say, of Open vSwitches. So but let's focus on the middle one, for example. And I apologize, but the lines kind of got hidden there, but all those lines actually point to the main one. The colored boxes at the bottom signify the connections to Open vSwitch. So think about those could be actual top of racks connected in, okay? And so you can have an OpenFlow switch connected in vSwitch, that exists today. We can have a normal Ethernet switch connected into Open vSwitch, that exists today. And now we actually have the ability of an SBB capable switch. By the way, every switch that's been shipped from the last 5 years has the ability to do this if your vendor has the ability to run SBB. And now that functionality is in SBB that we're adding here with auto attach is that we separate this model of what a client and a server is. And so the model we put into Open vSwitch is we put this client code. I am a client switch, and I want to tell the network infrastructure. So the network, the top of racks and the cores are all down below this. We're looking at a perspective coming from the vSwitch. So imagine applications are sitting on top. They're going to say, I have a new VM, and it's going to be configured down, coming down from Open Daylight, right? And it's going to configure the vSwitch, and that's going to tell the network what it needs, and immediately the service will deploy. Now, stepping back from that, we can use interesting things. You can use OpenFlow, you can use NetConf, you can use RESTConf as far as I'm concerned. But the actual discovery of that auto-attached server, this is where things got interesting and why we needed to do this project. It was all about scale. Because the normal operation of this thing happens is that any one of those switches in blue or green, anything you plug into a normal environment that has OVS and then you turn OVS into its controller mode, right? It stops acting like a switch. It acts like a zombie, essentially. And maybe that's not a polite way of putting it, but essentially what it does is it takes every single packet that needs to be processed and hands it up to its controller. Right? Everything has to be passed up to the controller. And so if you look at this from a perspective as what if I have 20,000 OVSs sitting out there and I've got all these LDP packets coming in? All those LDP packets have to come in, and now you're going to burden that controller, and you're going to deal with a propagation delay between client and controller. And you're going to have to process at the controller and then propagation delay back down. That's not a very interesting way of dealing with performance or scale. So what we added back into vSwitch was the ability that in controller mode, it could still do local LLDP to allow a distributed nature mixed with a controller nature to allow a high-end scale and improving performance at the same time. And so with that now is that this, you notice it says AALDP there in the middle. The green nodes operate the way they always operate. The first rule in everything you do in engineering is first, do no harm. Right? We did not affect any of the traditional controller ODL perspective in this thing. What we wanted was to add on to the existing one for people who wanted to run local LLDP. So this could be used for other things as well than simply our auto attach. And that when we discovered an LLDP packet coming into the vSwitch there, it tells the controller, and our controller tells the local switch, start enabling your local LLDP now for those ports connected to those devices. All the other green ones, the traditional ones, keep sending to me. Right? So now there's a differentiation and intelligence built into the system. And that allows us to do some pretty cool things. Now, what does this mean from a controller perspective in the plugin? Now, in the plugin itself, we added this distributed LLDP auto attach thing. Now, it's basically 3 functions that we have to worry about. Right? The first one is model it, consume it, and configure it. So on the first one, we're following the generic rules of how Lithium based on the MD-SAL. Right? So we are following the architecture that Lithium kind of put in place to say, okay, we're going to now do an abstraction model perspective with the MD-SAL. That was a very critical thing. Now we can use any protocol you want underneath OpenFlow, NetConf, RESTConf. I love them all, kind of thing. Choose what you want. For us, particularly when we first started prototyping this, we're using OVS DB. The next one is consuming it. And I'll get into a little more detail on the next slide, but it's a heavy text slide. So let's kind of approach this here. We also didn't want to make it where you could only use northbound or you had to be local to consume. So we're allowing both kind of capabilities. And then the final one is how do you interact with an LLDP node that's capable of doing the auto attach function? Is detecting that and then automatically configuring that was also a critical point. And configuring it in isolation of the other LLDP services that might already be running or need to be run in the future. And so we didn't want to create another binary application where it's one or the other. The traditional mode of OVS was it's either acting like a switch or it's acting like that zombie. Now in this mode, it can act both at the same time. Right? So to that point, do no harm, only improve. So we're trying to follow that in good community model. All right, so I apologize for the heavy text slide, but it's important to kind of consume this holistically. Is kind of look at this way. The next slide will be easier to digest with our graph and our architecture. So this basically kind of describes what the plugin architecture is going to be. And so essentially the first 2 bullets describe how we discover things. And so the first bullet we were talking about is that we will see an LLDP packet come into an OVS. I'm using OVS as an example because that's what we use. You can use your VM du jour adding this functionality. But we consume this information looking at that LLDP packet in. So the normal behavior happens first. Right? Every LLDP packet that comes in is sent up to the controller. And the controller now pays attention with the plugin when it's installed to say, oh, that's a specific type of LLDP. That port on that switch, vSwitch, now needs to run in a specialized mode. And so it'll send down the next to that third one, and actually down to the fourth as well. You need now to start actually paying attention and using local LLDP on that port you receive that on. And now I'm going to go ask either my internal policy or some external policy, however the northbound interface has been configured, which is that second bullet saying either you're going to configure it into ODL or you're going to come in and consume it and configure it through the northbound interface. And so we can have ODL pass through the awareness of a new auto-attach capable node out there to an external through ODL or inside ODL. That's been a really nice way of actually keeping this on a modular kind of approach. Now, once we have that information moving down to the third and fourth bullets there, right, we want to turn on that local LLDP, but there's a very important thing there is we need to make sure that the southbound interface is capable of this. Right? So that's why there's that coupling of OVS plus ODL is important here. The vSwitch and the controller work as a team. And that is that the controller has to know that the southbound protocol can support the carrying of this. And so that's why we use OVSDB in the first instantiation to actually carry this VLAN plus ISID information. Because if I were to ask in the beginning of the room how many of you actually know what an ISID is, I probably would only get a couple of hands. A lot of people didn't know that the IEEE invented a 16 million identifier for VLANs many years ago. In fact, the idea of using VLANs only was like a 1990 perspective versus 2015. And so we had to go into a lot of these protocols and add this ISID awareness. And so that's as we're going into this thing and looking at that. What gets really cool about this is that now the Yang models, and even the IEEE is defining new Yang models for VLANs and ISIDs and all that stuff, will be embedded directly into these environments. And so we'll actually take available of this. The consumption, by the way, if you kind of like read into the perspective of what that northbound API might be, is that could be OpenStack. That could be a homegrown application. It can be whatever you want. As far as I'm concerned, that could be an iPad. Right? That's the nice thing about the modularity of this thing is that you can plug and play anything at different places. And so architecturally, when you think about this, is that it's essentially any device there in the bottom left that can run LLDP can signal up to the SPB fabric through to the controller, and the controller tell the actual end device what to do. And so what this is trying to depict here is that, say, for example, an OpenStack virtual machine is now ISID aware as well as VLAN aware. Once it comes up in the environment, it automatically goes to its controller and through that interface to OpenStack gets its configuration and tells it to run LLDP locally. Policies applied to it. It says, okay, you belong into this virtual service and this subnet, and this is the LAN I want you to have. Now that LAN, instead of being just a VLAN, is actually a tuple of a VLAN plus ISID. Because I might want to reuse VLAN 100 from this service as well as on another service. So now I'm not stuck to 4,000 VLANs anymore in OpenStack. I've got 4,000 to 16 million power I can use to this capability. And I can do it at native hardware speeds using the ASIC on the top of rack, integrating with the virtual machine sitting down in the actual rack itself. And so once it's been assigned its capability, OpenDaylight downloads telling it that tuple. And what it's basically telling that VM to do is, here's your configuration parameters for what you need to configure for your virtual NICs. Here's the fib state for what you need to forward up to the actual hardware. And this is the join message I want you to send up to the actual physical top of rack. And the join message will be that LLDP going the opposite direction from the client now to the switch. And the client to the switch is saying, I'm going to send you VLAN 6. Please attach it to ISID 2 million. And automatically that SPB capable switch is going to see that, and on that incoming port, map that VLAN to the proper ISID, and from that point forward until it gets a change in the message from the client, it will always do that. Now what gets really valuable about that is because it's now being auto-discovered on that, we don't have to do anything special to the SPB switch. Notice I never touched, from OpenDaylight or anything else, the switch. I touched the edge device. I managed the device. And I'm able to do that in the order of tens of thousands too, to do this because we need to scale it because I'm actually configuring these things all the time. Now we're actually kind of looking through the performance of this thing because we're worried about how far we can take that because there's a lot of research going into how far can ODL scale. So we're trying to take from the first start, how can we take an architectural perspective that is a scalable solution so that we can help this and not hurt this in the future? And so the distributed nature of this thing is one aspect. How we don't send batch updates, things like we are going to send batch updates, we don't constantly poll, things like that are important things you kind of approach, and just how you manage that scale. Now that middle one's there, for example, is you can use OVS right off the shelf and play around with this and go. You can use kettle commands directly in OVS to do this without using a controller if you want, or you can use them in combination. But also things like video cameras, they all run Linux. Right? Your Raspberry Pis, a lot of the things inside this building here are all running Linux. Sensors are all running Linux, and they all have open source implementations of LLDP. In fact, we created an open source LLDP instance that actually supports this already, and we put that out in GitHub. Links are actually at the end of this. And so that they can actually implement this themselves and use their own management software. And that could be part of those northbound APIs that come in and communicate to ODL. And so that's a nice, powerful thing about mixing and matching and not taking a dogma perspective as that everything has to be centralized, is that by using this combination of centralized and distributed, we're actually able to do some pretty creative things and enabling markets that might want to use this in ways that they hadn't actually thought about in the past. And by the way, the cool thing about this is that this auto-attach capability doesn't necessarily always need to require an SPB network. If you just want to attach a VLAN to a port, there's logic that could be applied to that top of rack that simply says, I see a VLAN come in and the ISID's zeroed out because I'm not running SPB yet. I'll just assign that VLAN to this port. Now, it's only going to be assigned to the local port, so you have to have it locally or everywhere else, or you're doing routing locally, that's fine too. But if you want to actually be able to scale across the entire environment, the nice thing about this is that you can have that OpenStack on there and the security camera management software automatically sitting on a LAN. And as soon as these VLANs show up, the VM can be moved anywhere it needs to at any moment. And the nice thing about running this on an SPB fabric is that it automatically assigns and updates those fib entries at the hardware speed. Right? It doesn't have to propagate up and then download to all the switches in the middle. The link state protocol automatically sees the new join and automatically rewrites the fibs on the fly. And since it's one protocol, I can write this at incredible speed versus a multitude of protocols trying to write and compete for CPU and memory resources. Right? So that was actually the whole presentation. It's a very short it's a very simple kind of presentation. If you actually want to play around with this or kind of read more about it, there's a couple of places you can go. For the start, to kind of look at what the protocol itself is, you can actually look at that draft that we put into the IETF. We'll be submitting a new one here soon. And it's a good way in which we were socializing the idea around a community of interest throughout this. And we have several other vendors kind of looking at this at the same time. Given that that's the IETF, though, and this is an IEEE protocol, we moved the work completely into the IEEE, and it was approved for PAR recently, and it's now 802.1 QCJ, as I said earlier. And so it'll be part of the base Ethernet spec that anyone can use. So what was important to this for us was we didn't want to just create a de facto standard. We wanted to have a facto standard, one that actually was a reference architecture that could be implemented not only in software but also in hardware and make sure that both would work together inherently the way that the last 30 to 40 years of Ethernet has worked so well together. Right? And so if you want to get a little deeper into the actual ODL capability, I embedded the link there. You actually can look at the repo name. It's AALDP. This is, from what we were told, this is the first time actually this approach has been taken in ODL, is to take a distributed plus a centralized management at the same time and kind of work them together. And so if you want to look at the OVS capability and how you actually do the local LLDP, you can download the code itself directly off GitHub. It's very simple. It's github.com auto-attach. It's free. We've been surprised how many people actually emailed us asking about certain calls and APIs because they're implementing it in the background. And so there are two things in there in which the way we did it. We tried to create a complete reference architecture. We didn't want to leave anything to surprise or have there was no obfuscation. It was completely open in how you would use it. And we also realized is that not everybody's going to want to do the full-blown OVS. Some people are just going to want to run their own LLDP. For example, why would a surveillance camera need to run a vSwitch? It just needs to run LLDP. And so up on the GitHub site, we put just the LLDP functionality. It's a very stable. In fact, the OVS guys helped us. We had a lot of back and forth about how we could stabilize and actually improve the code itself. We cloned that actual LLDP instantiation, added the auto-attach capability to its LLDP, and so you can download it and use it yourself. And then the full SDK has a working server to the client, which is useful so you can actually virtualize the server functionality and actually test it without having to need a physical switch, which was important for a lot of us software developers who don't happen to have a fleet of switches sitting behind our desk or don't want the noise behind us at least, right? So this allowed us to, to virtualize and optimize a lot of things as we were going. So everything out in the open, trying to be good community citizens in our approach to this thing, not trying to do proprietary open source, as some people would call it. This is actually everything out in the open as we possibly could. That's actually the full presentation. If there are any questions? Start there. You had your hand up first. Good. I don't know if they're making them available. They're recording all the sessions, so I'm going to assume that they're going to make the slides available as well. I'll ask you can ask the ladies up front. I'm going to ask them as well.
Very smart. Congratulations.
Thank you. What's that? Okay, so yeah, it's funny you went right to active-active. You might have noticed that I put 2A servers down there, primary and secondary. So part of the original scope of what we're doing is that we are going to work towards an active-active. All right. There's actually a protocol inside the IEEE called DNRI that does an active-active functionality. Right? There's a lot of capabilities inside vSwitches that already support the active-active as well. And so we didn't want to kind of prescribe the method of doing it because every vendor has a proprietary way of doing it. There's now a new standard way of doing it. The VMs have a way of doing it. And so if you have all these competing ways of doing active-active, we can't prescribe a way of doing it. We just simply wanted to have the ability to announce the attachment of a VLAN. Now, if you're a halfway decent software developer and you know your own implementation of auto-attach, of auto-attach and of dual homing in an active-active model, so you're not primary-secondary but primary-primary, you can very easily realize that, well, if I took my CLI configuration calls, that I would configure that, and I mapped it to this protocol call, I can match them together very simply. And so that's kind of the model we were trying to like guide people towards. Is that this does not preclude active-active. It does not force a primary standby. It can use both at the same time.
How about layer 3?
Sorry?
How about layer 3?
Oh, layer 3 routing? Okay, so that's a fundamental thing actually about SPB that actually integrate there. So this ISID is a VLAN, right? And so when you think about, so this virtual service network, this ISID thing we have here, it's a LAN. It's no different than any other LAN you knew before in concept, except now it's actually flexible and scalable. So you can actually take that ISID and plug it into a routing context. That's what a lot of vendors do, right? So it becomes, just like you have inter-VLAN routing, you have inter-ISID routing. And in cases where I know of actually plugging into a router that doesn't support SPB, you just map it to a VLAN and that router just routes between VLANs. And so while you're going out of, say here, for example, say there's a router on this far side here, and I've got these two LANs going out, and that could actually stretch out to hundreds of points. The router sees VLAN 200 and VLAN 120, and simply sees those two subnets. It's the default gateway sitting on that. So it can be a physical router, or it can actually be a routing context in the middle of that cloud. Yes? Yeah. No, so VRF actually becomes more intelligent about this. So I think we need to get you a mic because I'm only hearing half of what you're saying. So I think what you're saying, and tell me, correct me if I'm wrong, is that because it's a 4,000 VLAN versus the ISID and that the router doesn't understand the ISID, it actually loses visibility into all the subnets. Right? The reality is no. All right? Because of the way in which we've seen a lot of deployments connecting to VRFs running on SPB, the ISIDs are aware. The actual routing context for us, I don't know how other vendors are doing it, but you distribute out the routers separately. So just because router 1 sees VLAN 16, that VLAN 16 can mean something completely different to router 2. Right? And that distributed nature of that allows you to scale this up to that 16 million functions. Because you're not going to run 16 million on any given node, but holistically in the entire network, it's a probability you could be running a few million. But because of the location of where the routes are, and the nice thing about using VRFs with these ISIDs is that now I'm able to reuse the same subnets and private subnetting space inside the VRFs. Right? And I'm able to do true multi-tenancy of layer 2 and layer 3 at the same time. So for years, all that stuff that we learned out of MPLS can be reapplied directly in a metro, a data center, a campus, using the same similar techniques of VLANs and VRFs, but without all the baggage of MPLS. Right? But the nice thing is because it's VRFs, it's not a choice. You don't have to choose MPLS or SPB. You can actually connect them together. And there are live deployments that do that right now, where a VRF in the SPB land connects to an MPLS VRF. Right. You got a question, Mike? Yeah.
The OVS source code?
Yes.
It's a modified OVS?
No, it's in the main line. In fact, when 2.4 releases here soon, and we don't know when that soon will be, right? It's up to Ben and others. Yeah, 2.4. It's in the mainline 2.4 release. It's right there. Right. Yep, absolutely. Let us know if you play with it. Let us know what you think. If you have problems or you love it, we want to know both ways. Okay. Anybody else have any questions? Okay. Oh, sorry, I didn't see your hand. Sorry.
Just curious, this thing seems to scale pretty large.
That was the intent.
Well,
Yeah.
how large? Could you do the entire US telephone system with this?
Oh God, probably not. I don't think any protocol can do that. It's hard to actually say what scale is because scale means so many different things to so many different people. Like a scale to a large CSP, a cloud service provider, is going to be different to some of the ILECs, for example, right? And it's because they're different at looking at different things. From us, from a perspective of scale, was first, we already know that we have to deal with the traditional scale issues of a server running on a physical server, like server software running on physical servers. We didn't want to make that worse. We actually wanted to improve it. Second is that, I mean at the controller space, that is. When we started playing around with this idea, this auto-attach function, and before we did it local, what forced us to drive local was the fact that we had all of these possible things that could be connected in, and we were able to simulate all these open vSwitches. It was really easy to simulate. It was very quickly apparent that trying to send all those LDP messages funneled up to a controller basically was a denial of service attack. Right? That's essentially what it became. All right? And so we had to rethink, step back, and we had to basically eliminate dogma. Now, dogma is centralized, right? Well, if we actually just think as engineers, why have dogma, right? So that's the scale question you pointed out there was, okay, how do we scale it? How do we actually use these things together, centralized plus distributed? And so we moved the LDP that we are capable already, put it right into the module, the plugin, down at the Open vSwitch, and KVM can use this, VMware can use this, whoever wanted to use it. What should happen then, or it becomes a matter of how much can you scale, or the CPU and the memory you put to the controller versus how much you actually can put down at the edge. And so I can't really say, can I scale this out globally? Yeah, you probably could. I don't know what the performance is going to look like in that model, right? But can I do 5 data centers doing a multi-tenant hosted? Yeah, actually I can. I know I can do that pretty well, right? Because the fabric that's in the middle of this, by the way, if I go back to what this looked like, that is already hosting some very large environments and doing it at some incredible speeds, right? So we're seeing those clouds reconverge in milliseconds, network-wide, right? So an outage in the middle of that network means the whole network is converging in less than 100 milliseconds. Well, the human ear can't even pick up a problem with a voice call until 350 milliseconds. So oftentimes we're seeing the cloud in the middle reconverge faster than the applications even know there's a problem. Right? And so by tying that then to the client devices out there who can automatically signal to the network, so you'll notice there's a lot of distributed on top of distributed in this thing. We're trying to use the modern volumes of what we've learned in computer science of centralized policy, centralized configuration settings, distribute out the awareness and the healing of that, and then the awareness of the configuration. So we can couple together. It's kind of a roundabout way, a long-winded answer. Hopefully it gave you a view. I can't say it scales to this number because it really matters what you're running it on.
So the congestion point would be the controller.
Yeah, it always is.
So what is the controller doing in this situation?
So let me step back and kind of dig into this a little deeper. So the controller in this case is doing a couple things. First, it's processing all the packets that come out of this box. So the green, for example, there. So before the local LDP happens, today, 2.3 OVS or any other VM, right, vSwitch you're running, it's going to have to process all the packets that come out of this thing before the forwarding rules are set there. So control packets have to be sent up to the controller. So that's the first thing. We all know that, right? In this model, what we happen in a lot of deployments, we don't see or perceive there's going to be a lot of open flow switches, but we do think there are going to be some. And so we want to make sure we have that flexibility to add it plugged in. The LDP packets no longer get processed there. The only thing that the actual Open Daylight server, and this is where I'm actually very positive in my think of how this is going to scale, is that it's only doing things when new things happen. And that is a new VM appears, a VM needs to be moved, or a VM disappeared. CRUD, basically. So depending on how much CRUD applications you have in your environment, depends on how much work the daylight controller has to do, the ODL controller has to do. Right? And even when it's doing something, it's not doing a lot. Right? It's not trying to process and download massive states of information configuration. Right? It's downloading 2 sets of information. The fib rules from the virtual NIC to the virtual NIC going up to the actual physical switch, and it's downloading, telling a simple tuple of VLAN ISID. Tell your locally connected a server switch, this is the information you need. And then that little message carries a tremendous amount of weight with it because it automatically causes the entire infrastructure underneath to reconfigure itself for the virtual machine or the IoT device in the campus, right? And by doing that, you offload the controller from having to configure 1,000 switches between two endpoints, right? And so I think we're going to see some pretty impressive scale on this. That make sense? All right, make sure I wasn't confusing you more by my long-winded answer.
I was just thinking, what if that was you fill the data center with all those controllers, distributed them around
Sure,
the
yeah.
AT&T network?
Yeah, that's highly probable and possible. And that people will want to distribute. Every time you do a management server, the next thing we do is we do distributed management servers, all right? And that's just been the history of life in all these systems. And I highly expect that's going to happen. Right? We'll probably end up seeing regional or service-based kind of a perspective on that. Right? Anybody else? All right, I appreciate you sitting this long at the last session of the day. All right, have a good show and have a good night. We've went from 0 to 40,000 users in less than 12 hours. That was a drop in a bucket compared to the actual total number of devices connected to the network. Total number of devices in an environment actually numbered in the hundreds of thousands. So users were a tiny little blip on our screen as far as devices we had to worry about. And by the way, those 40,000 users were bringing in 3 to 4 devices. Right, so really it was 120,000 devices. Still, that was not a small amount of the traffic we worried about. The large amount of traffic we're worried about is the trash cans that were connected to the network, the clock that you were watching the games on, right? The camera, right? All these little things that are connected inside this environment actually needed real-time applications, and those things would not accept an amount of downtime. And then if I look at a hospital, they have the same problem. Stock exchanges, the same problem. Subway systems, exactly the same problem. And the idea that our networking staff would be able to actually go out and configure every port on the fly for every device was untenable as well. It would have taken a fleet of people years to do. And so by taking more of a Fabric plus SDN approach, we were actually able to do it with 2 people in the NOC only. For the entire event, 2 people, that's it. And so it's kind of like running 7 Super Bowls every day nonstop for 3 weeks. Now this is not special to Linux. I just use them because they're a public example of all the other deployments that are out there. But it showed why we needed to solve this problem. IoT is no longer a buzzword. It's a real problem in real environments that we have to solve as a way of getting the humans out of the machine and make them more of the policy drivers. And so policy becomes a critical component of it on a scale. Right? And so LLDP and all these other protocols, trying to get all the LLDP messages coming up and bridge that up into a centralized place works up to a certain point. But once you start getting into the level of hundreds and thousands and tens of thousands of these devices out there, you start running into issues about how you're going to scale that and manage that in a large-scale environment. Additionally, what we found is in a lot of deployments around the world of a protocol we called SPB, which is down there at the bottom, AD201AQ, is it's used in a lot of data centers. It's also used in a lot of campuses. And we found that it does a lot of the automation and capability that a lot of data centers are asking for. And the last piece that was missing was the ability to automatically attach the edge devices directly into the fabric. And now, so some vendors are taking a perspective of, well, let's just abstract that by creating overlay tunnels. This will actually allow you to integrate that into this thing. But SPB actually gives the same functionality directly at the hardware level. Right? You actually have complete virtualization. We're not limited to 4,000 VLANs anymore. We actually have 16 million. And we have integrated routing in it as well. So with those capabilities, we're actually able to forward and create LAN environments, anything we want, across a physical infrastructure and do it in a couple milliseconds. So you just configure one end, you configure another end, and the network automatically creates a LAN in the middle, irregardless of the scale. This isn't 4,000's tiny little data center networks anymore. These are now very large-scale environments. Now, the scope of where we're trying to get to this thing is kind of described there. Is that I'm going to go ahead and start conversation here. So this is based on a project that we started earlier this year, and I'm going to kind of give a background on why we started it, what its functional capabilities are, and why we had to do it. And so let me jump right into kind of that agenda perspective. So I'm going to start with the what. What is the project that we started with in ODL, why we did it, why it's needed, and then jump into how we're actually implementing it. I've seen a couple of the sessions here with actually pulling up CLI and running demos. I'm not going to do that. I'm just going to give more of an architectural kind of perspective on this. This has been a rather interesting experience for us as we're new to ODL. We've taken this approach second after doing a lot of work with Open vSwitch and the team members there throughout the experience of developing that has been a lot of fun. And as we got the implementations of OVS done, and that's now part of the upcoming 2.4 release for this functionality, we've had to now move on into the controller space to make sure that we can get a holistic management of that. All right, so let's kind of jump into the project description. So what we started was basically a way of managing a distributed LLDP approach. Normally, the way ODL will actually work is that anything that happens as communication between the vSwitch and any of its actual physical switch neighbors has to all be sent up to the controller. And while that's a nice way when you want to know exactly what's going on inside the virtual topology, and you want to have an ability to control that topology, it also creates a tremendous problem. We want to be able to configure the actual vSwitches to tell the network what service they want delivered at their point. Because oftentimes the network infrastructure in place is not owned by the same team that's deploying the vSwitches. Now, the network team itself is not actually managing the vSwitches either. And there's always this kind of separation of the two environments versus the actual management of the environments. And so if you had the ability that a network could be created, stabilized, can deliver any service anywhere at any moment, and then the applications and the virtual machines themselves can be turned up, moved, deleted in any combination, and automatically signal to the network that they need a CRUD application happen to create, update, or destroy kind of operation, then the network would automatically deliver that and deliver it within milliseconds, and also deliver streams of connectivity in milliseconds without affecting performance. You've got a good, powerful thing there. And so we worked with a few entities out there to try and make sure we approach this thing as open as possible. So we tried to make sure that we were being very good open citizens. So we used open standards. We actually took the idea of how we would auto-attach these things to the network and created a pre-standard, long before pre-standard, actually, an idea and put it into Open vSwitch, so it became open source. We actually published a draft into the IETF. You can look it up by my name. And that draft has now become 802.1 QCJ in the IEEE. And so this will actually become a standard part of 802.1q as a way of automatically signaling from a VLAN or non-VLAN capable device, because it doesn't have to be a switch, a vSwitch. It could be, for example, an Internet of Things device that simply can run LLDP. And that will automatically signal to the network that it needs a service. And so a use case of this thing is that kind of we discovered over some really large deployments and even small deployments. At the Sochi Olympics last year, we discovered this ourselves as we deployed this. This is one of the more public examples of shortest path bridging running in the wild with this entire network. Everything you watched, if you watched the Olympics, by the way, was running over SPB. There was no MPLS, there was no OSPF, it was all SPB doing the routing and the switching. And it showed us a lot of things because it's a great example of the modern day environment, both data center, campus, and metro, is that virtualization is no longer a nice to have, it's a requirement. There's a lot of concepts and discussions about what microsegmentation is. If I look into a hospital, for example, there's a ton of microsegmentation. The MRIs, for example, are locked away from the pill dispensers, which are locked away from your guest wireless. Those are great examples of true virtualization have to be enabled. And they can't come at the cost of an MPLS core, right? They got to be done quickly and at hardware level and managed centrally. And so that's that nice combination that we see out of a Fabric plus an SDN. It shouldn't be a Fabric or an SDN. And a lot of the customer deployments we've seen out there, that's exactly kind of the case. But when they're looking at the world of what are they actually trying to do versus just a cool technology, well, the cool technologies are fun for us to play with as engineers, but they don't actually solve a business problem. And so the business problem we're trying to solve is how do we automate the attachment of these devices because they're exploding. And at the Olympics, a great example.